Time to do some more probability. Now, this is what we've been doing before has been more kind of standard textbook probability problems. Now we're going to, which is definitely on the IB exam, but now we're going to deviate from the textbook and really delve into what IB is going to expect from you. And again, don't stress about whether you really, really internalize this stuff because you're going to see almost all of it again within your higher level class, because it'll have been a whole year. When we do in calculus, we'll do none of this. So it'll be a whole year when you sit in your HL class. So Mr. Davis will start you basically from scratch with all of this. So discrete random variables and expected value. Now, expected value is something you're going to see again in the next video, in the next lesson. But right now, I'm just going to introduce expected value and a formula for it and kind of conceptually what it means. And then really, this is really old news, but with new notation. And I talked about this before, this word discrete. Think discrete, think counting, think curly set 1 or 0 to 1, and there's nothing in between it. We have really been dealing with discrete random variables, pulling a card, rolling a die, right? Someone sitting in a seat. That's really all been discrete. Not all probability problems are discrete though, right? We can have some continuous situations, but everything we've been doing has been discrete. So remember that the probability of an event that's not equally likely, best example, rolling the die. It is not equally likely that I roll, if I have 2 die, that I roll snake eyes versus rolling a 7. So we talked about the probability of the event, for instance, rolling a 7, is the sum of the probabilities of all the outcomes, given that I have a probability distribution. And remember the requirements of a probability distribution, right? All the probabilities have to sum to 1, right? And each of them, right, that we have the total after we figure out what the distributions are. But in reality, there are 2 different types of distribution functions. And remember, you've got a whole lot of math that you know that is function-based. So the probability distribution function, PDF, oftentimes it is in textbooks or whatever, which is funny because PDF also, I think PDF is, right, a file. Anyway, probability distribution functions really can be continuous or discrete, right? The data can be continuous or discrete, but as soon as you are talking about actually just discrete, probability mass function is more appropriate. The probability distribution, this is just much more commonly used. And why is because it can be either referring to continuous or discrete situations. But the probability mass function is a discrete, which is what we've really been doing all along. The same requirements, but different notation. The function, the probability function, assigns a real number to each outcome in a sample, and here are the requirements. Each probability is between 0 and 1, and the sum of all the probabilities is 1. Here's the notation, though. Usually capital P, but not always. Sometimes this P is a small p. But they say the probability of a discrete event is X, and then they give you a list of X's. Don't always put the squiggles around it, but I think squiggles because I think discrete, there's nothing between 1 and 2. That is different as X being an element, right? That's continuous. All the numbers between 1 and 5. So when you see this expression, 2 to the X is 62, I can put any number in for X, right? 2 to any number, all real numbers. But with the probability mass function notation, this X has to be defined with a discrete list. Now, the discrete list can be infinite. I could say 1, 2, 3, 4, 5, dot, 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 but it can't be continuous. This is continuous notation. This is discrete. So I say to myself, self, here's my discrete random variable. I expect a list that's going to be my input. And then I ask myself, is this a PMF, which I could also call a PDF? Is it? How do I check? Well, I'm going to input all of these, right? So I'm going to say 2 to the first over 62, 2 to the second over 62, there's all the probabilities. Those probably certainly are between 0 and 1, right? 2 out of 62. This is 2 to the fifth is 32 out of 62. Now, is the sum of them equal to 1? Well, they all have a denominator of 62, so I can just put all these. So 2 plus 4 plus 8 plus 16. Gee, what is that? 4 and 2 is 6. It's 14. Plus 32. What is that? Oh, that is 62 over 62, which is 1. Yay. So yes, the sum of the probabilities is up. So this is a PMF. So here's a more traditional one, right? This is the one that we were used to. I just didn't use the notation on it before. So again, this is old news, new notation. The probability of, here's my discrete random variable, right? So my discrete random is X. Here's my X. So plug in 2 for this situation, and I get 1 out of 36. 3, 2 out of 36, 4, right? And we talked about how we came up with these 1 out of 36, right? That's multiplication property of probability. Old news, new notation. Here's what the probability is. Is it a probability distribution? We already figured these out. So here is the question in English. Here's the same question. It's the same question, just with new notation. What is the probability of, from my distribution, of X being greater than 8? Rolling a sum greater than 8. I just have to add those together, right? It didn't say greater than or equal to, so the probability of 9 plus, plus, plus 7, 8, 9, 10. Reduce if you want. Okay, and that's all I did. I know you don't have to write that all out. So probability that the discrete random variable I put in is 9, 4 out of 36. Probability when the discrete random variable I use is 10, 3 out of 36. Right? That's all I did. So again, think of the discrete random variable represents numbers found by counting, not an infinite situation. Numbers, so we've been doing all this, right? Oh, I have blue marbles and green marbles and blah, blah, blah. Oh, I have a number of students present versus number of students absent, or the number of heads when tossing 2 coins, blah, 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 blah. All of that really is discrete random things, right? Again, old news. A discrete probability distribution has the discrete variables, that list, right? Rolling a 2, rolling a 3, rolling a 4, tossing a head, getting a blue marble, students in the room, and the associated probabilities with it. So here's a good example that IB would ask, right? And if you just read that problem, if you don't understand the notation, you're like, I don't even understand what's happening here. I don't even know what's being asked. So, and do they love their little Greek thingies, right? So the probability when my discrete random variable is 0 is alpha. The probability when my discrete random value is 1 is 2 times alpha. Probability when my discrete random variable is 2 is 3 alpha. Can you find alpha? What are you going to do? Well, what do you know about a PMF? You know that each of the probabilities has to be between 0 and 1, and you know the sum has to equal what? 1. So you take those probabilities, A, 2A, alpha, 2 alpha, 3 alpha, add them together and set them equal to 1. And all of a sudden you have an algebra 1 situation. 1 plus 2 plus 3 is 6 alpha. Therefore, alpha is equal to 1/6 between 0 and 1. Is 1/6 plus 2/6 plus 3/6 equal to 1? Yes, it is. Very simple problem, but if you don't understand the language, you have no access to that problem. So look at this one. Somebody's given you a chart with new notation. So this is your list. And these are your probabilities. The probability when my random variable is 1 is 1 out of 10, 2 out of 10, 3 out of 10, 4 out of 10. Now, I want you to think about this. I don't even know where this table came from, but let's say it's an experiment. So whatever 1 represents, the probability of me achieving that event, when x is 1 is 1 out of 10. But whatever x is, when it's 2, well, I got a 2 out of 10 chance of that happening. 3 out of 10 chance. When I use 4, I have a 4 out of 10 chance. So let's suppose I repeat this event over and over and over and over again. Which one of those values of x, right? Capital X, not the probability. Remember, x is equal to that list of x's. Which value of x is the most likely? Think about that. Well, certainly not 1, right? The likelihood that I get a 1 is only 1 out of 10. So if I repeat whatever this experiment is it rolling a die with 1, 2, 3, 4 on it? Is it pulling a card? Whatever it is, over time, which event is more likely to occur? Again, this is the lowest probability. This is the highest probability. But I do have some low probabilities. So what do you think? What I just asked you was an expected value question. Think of expected value as the mean value, but not the mean of the probabilities. The mean of the random variable. So you can't just say 1, 2, 3, 4 divided by 4. What do you think this means? Mean, get it? The average value, the expected value, is an average, it is a mean of the random variable if you repeat the experiment multiple times. So in order to figure that out, as long as you have a discrete random variable and you do have the probability distribution, meaning your probabilities add to 1 and each probability is between 0 and 1 inclusive, The expected value of the random variable x, not the probabilities, is this formula. OMG, pull that out at parties. So people say, oh my God, you're so smart in math. But it really ain't no big thing. I gave you this notation because your calculator uses it. But the expected value of the random discrete value is a sum. Capital sigma means sum. A bunch of products. Sum a bunch of products. What are those products? This is each, see that little I stands for individual. Individual x in your list times the probabilities of each individual x. And that should make sense, I think, if you think about it. So what they're saying is that the probability of event 3 is 3 out of every 10 times. The probability of event 4 is 4 out of 10 every 10 times, as opposed to 2 and 1. Multiply these. Multiply. 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 Then sum. Sum all of those products. That's all this says. Sum the products. NBD. So what do I get when I do that? Let me erase some. Well, no, I don't. I guess I don't need some erase. So what is this? This would be 1 times 1/10 plus 2 times 1/10. No, 2/10, silly. So now remember, you're getting an expected value of the random variable. So what do I have here? 4 plus 1 is 5. 5 plus 9 is 14. 14 plus 16 is 30. Over what? What value is that? That's not a probability. You're not summing to 1. That is saying that if you do this experiment over and over and over again, the expected, the most likely outcome that you're going to get is a 3. It's not exact, right? I know it came out very nicely to exact, but over and over and over again, sure, you're going to get a 1 sometime. You're going to get a 1, 2, 3, and 4 sometimes, but the most likely expected value is a 3. And hopefully that makes sense. Oops. Forgot I wrote that out. Look how fancy that looks, right? This looks so fancy. But I'm just saying, okay, so each individual x is the first one, the second one, the third one, the fourth one, the fifth one, the nth one, right? Each individual x times its probability. Add them up. So here's a great example. Expected value is a nice thing for this game of chance. This, believe it or not, this math, this probability, this thinking is what happens on Wall Street all the time. Happens in stock market, happens with housing, certainly happens in Vegas. Right? Not with a coin necessarily. And of course, it's more complicated, but this is what's behind it. So I flip a fair coin, so it's not weighted or anything. And every time I get a heads, I have to lose $1. And every time I get tails, I win $1. So look at how I constructed this table. You could be asked to make a table. So pay attention. Given information, you might be asked to create this table and then answer questions. So look at what I've done. Discrete random variable, because I'm tossing a coin. What do you think this means? The probability of getting a head or a tail is even, right? Every 1 out of 2 times I'm getting, right? 1 out of 2 is my probability of getting a head. 1 out of 2 is my probability of getting a tail. So this is my head situation. And why do I have a minus? Because I'm going to lose $1. This is my tail situation. This is the probability, but I gain $1. What's the expected value? So the expected value is just a right? It is just a sum. -1 times 1/2, +1 times 1/2, right? Multiply, multiply, sum. Whoops. Well, that's -1/2 and 1/2 would equal 0. What does that mean? What does that mean? Think about what expected value is talking about. It's not talking about tossing the coin once or even twice. It's talking about tossing the coin many, many, many times. And maybe you lose $1 10 times in a row because you just happen to toss a head 10 times in a row. But if you do this 100 times, how much money can you expect to win? Does that make sense? Because you're going to lose and gain. Expect it, not exactly, because maybe you only do it 10 times and then you're down $10 if you happen to toss a head 10 times. But expect over many, many, many trials that you're going to come out even. You're going to lose as often as you win. So that's what this question is. It's an interpret question. Given that you play this game many, many times, should you expect to win or lose money? Oh, it should say lose, not lost. Lose money over time. And your justification with that would be my expected value of X, I probably should put square brackets, but I didn't, don't care, is 0. Therefore, if I do this many times, I should break even. Right? So the game might be fun to play. I might enjoy it, but if I do it enough, I'm neither going to lose nor win. So think about it in our live session, maybe I'll change that up a little bit, right? I'll say I won't make this as even. Think about what, right? Because certainly the probability still stays 1 out of 2, right? So look at this problem. So I'm going to kind of jump from this very simple problem to a difficult problem, but in the live session, we'll do one in between. So look at this. I'll give you a minute to write it down. Could you? As you're writing that table down, think about how I came up with those values. Or even if you didn't make it, let's say it was given, can you interpret what each one of those entries means? So certainly you know what this is, right? I have a discrete situation. Hopefully by now you're used to this notation. X is my list of values. So this was just given to me. The probability of winning $200, why isn't 200 in my table? Well, because what this is, what does this say? This says you have a 1 in a 1,000 chance, not of winning 200. Why? Because you bought a ticket. You had to lay out $5 to begin with. So you take $5 from your pocket and you put it down. You have a 1 in 1,000 chance of winning 200, but you already spent 5. So really your winnings, this is your winnings. You won 195, but you spent 5. If you lose, you're down that $5 because you put that $5 out there and you ain't getting it back. So that's where these values come from. And then what they're telling you is, can you fill this in? What do you know? Well, what do you know about? Now, they didn't say it, but the only way to figure this out is if you're assuming that with this notation, you do have a probability mass function. So what is true? This has to be, right? Because these two have to sum to 1, the sum of just this row, the probability row. So what are the expected winnings for someone entering this? Oh, keep writing my capital sigma. Multiply, multiply, and then big sum. And add. So I did this on my calculator, and I got not 4.8, I got negative 4.8. What are the units on that? What is the expected value of again? It's not probabilities. What is the expected value of? So what does that mean? Basically, it means if you play the lottery, you're going to lose money, right? Which is why lotteries sound so attractive. But you can expect, right, that every time you plop down $5, right, you're losing $4.80 of it. Bye-bye. Just kissing it. Bye-bye. Believe me, nobody that creates a lottery creates it in your favor, right? Same with Vegas. The games are always in the house's favor. You're going to win. People are going to win. Absolutely. Some people are going to win big, but your chances of that happening, very, very low. All right. So we will do more of this in our live session. Talk to you then.